Hello everyone, my name is Igor Tayan and I will present the results of my paper entitled Characterization of Large-Scale Parameters in Indoor Terahertz Channels Applying the Ray Tracing Method at this year's workshops on communication networks and power systems. First, I will present an introduction about the research and the final contributions of the paper. Next, I will briefly describe the ray tracing method used in this work and the methodology applied to characterize the diffuse scattering, which is an important phenomenon for propagation in the terahertz range. In the following section, I detail the channel modeling and parameterization applied in this work, and finally, the simulation results and the conclusions of the work are presented. The future 6th generation networks must provide peak data rates on the order of terabits per second. For this, the allocation of communication services in the terahertz band ranging from 0.1 terahertz to 10 terahertz is seen as one of the main strategies to meet the data rate requirements of 6G systems. This spectral band has extensive available bandwidth, which can vary from tens to hundreds of gigahertz depending on the length of the links. The propagation in the terahertz range suffers from severe frequency-dependent losses, low diffractive capacity, and is susceptible to diffuse scattering. The development of the terahertz communications fundamentally depends on the adequate modeling and characterization of the channel. We present analysis of the communication channel in the range between 0.2 THz to 0.3 THz by means of ray tracing simulation results in an indoor environment. To characterize the propagation in this frequency range, the following effects are considered. Reflection using the geometrical optics and the Fresnel reflection coefficients, diffractions using the uniform theory of diffraction, diffuse scattering using the Beckmann-Kirchhoff theory, and atmospheric molecular attenuation using the ETU recommendation. The contributions of this work are analysis of the contributions of each propagation phenomenon to the multipath composition, the modeling of the distance-dependent path losses, and the statistical parameterization of the following larger-scale parameters: the rise factor, the shadow fading, the root mean square delay spread, and the coherence band. In this section, I will introduce some of the basic features of the applied ray tracing method. The applied ray tracing method is based on the shooting and bouncing rays. This method follows three main stages: the transmission stages, where multiple rays are launched for a given ray source. In the tracing stage, the rays' lengths are gradually increased and it's evaluated whether the rays interact with objects in the environment. In the reception stage, spheres are delimited around the receiving points. If a ray intersects a particular sphere, its contribution is incorporated into the channel impulse response of the respective link. In our methodology, three types of ray sources are considered: transmitting antenna source, the diffraction source, and the diffusing scattering source. Considering the aforementioned propagative effects, an arbitrary ray contributes to the channel impulse response with a normalized power described by equation 1. In this section, I will briefly describe the methodology applied to characterize the diffuse scattering using the ray tracing method. The Beckmann-Kirchhoff theory solutions for the average scattered power are valid under the assumption that the incident wave is in far-field conditions. To satisfy this condition for short-range links in indoor environments, all surfaces illuminated by first-order interactions are subdivided into sections with areas that satisfy the far-field condition. The diffuse scattering rays are transmitted for the centers of each section. The area of these sections is calculated according to equation 2. According to the Beckmann-Kirchhoff theory, the average scattered power is calculated as described in equation 3. In this figure on the right, the basic geometry of the diffuse scattering is illustrated. To apply the ray tracing method, it is necessary to describe the propagation environment. The simulations were performed in an indoor environment that can be classified as an office. This environment is composed of 5 different materials: concrete, wood, glass, metal, and plasterboard. The link characteristics are extracted from the channel impulse response. Considering that the received signal is composed by a superposition of multiple rays, the link channel impulse response and the channel power spectrum are described by equations 4a and 4b. The distance-dependent average path loss is modeled by means of the closing free space reference model, which is expressed by equation 5. Using the closing free space model in the channel gain data, the link shadow fading is calculated using equation 6. To characterize the channel in the terahertz range, the rise factor, the root mean square delay spread, and the coherence band were calculated. The rise factor, defined as the ratio of the line of sight power to the scattered power, is found in using equation 7. The root mean square delay spread, which is a measure of temporal scattering induced by the multipath channel, is calculated according to the equation 8. The coherence band, defined as the bandwidth over which the channel has strongly correlated spectral components, is calculated by equation 9, in which ρ is a correlation parameter. Often the correlation band is approximated by inversely proportional relationship to the root mean square delay spread, as shown in equation 10. In this equation, the kappa factor is a constant greater than 2 pi divided by r cosine of ρ. Now we will present the results of the ray tracing simulations. In this table are presented the simulation specifications. In the simulations, two transmitters were considered at a height of 2.4 meters. The receiving points are distributed along the propagation environment at a height of 1 meter. Channels were analyzed on 11 different carriers between 0.2 THz to 0.3 THz with increment between adjacent carriers of 10 GHz. To measure the contribution of each propagation phenomenon to the link composition, the relative gains were calculated as expressed in equation 11. This table shows the average relative gains of the channel at 0.2 THz. It was observed that the diffraction is the phenomenon that least contributes to the link, with a relative gain of minus 31.3 dB on line-of-sight links. This figure on the right shows the curves of the relative gains as function of the frequency. These curves are normalized to the respective values at 0.2 THz. It can be seen that the contribution of the diffuse scattering in the links increases with the frequency. According to the results, for non-line-of-sight links at 0.2 THz, the path losses propagation exponent is equal to 4.7. This parameter increases with the frequency, reaching a value of 4.8 at 0.3 THz. The standard deviation of the shadow fading for non-line-of-sight links at 0.2 THz is equal to 8 dB, ranging up to 8.6 dB at 0.3 THz. According to the data obtained in the simulations, the rise factor has an average value of 8 dB and a standard deviation of 4.12 dB. As shown in the figure on the right, these statistics grow with the frequency. Finally, it was observed that the average delay spread values are 1.5 nanoseconds and 2.6 nanoseconds for links with and without visibility, respectively. These statistics remain constant over the evaluated frequency range. The average value of the coherence band on 0.2 THz line-of-sight links is 330 MHz. This value is about 1.7 times higher than the one observed in obstructed links. In summary, the conclusions of the work are: according to the results, diffraction has a small contribution to the link composition and can be neglected in the channel modeling. The impact of diffuse scattering is relevant and its contributions increases with the frequency. The growth of the rise factor mean value indicates that the effects of the scattered components decrease as the frequency increases. It's also observed that the average coherence bandwidth in line-of-sight links is about 1.7 times greater than than that observed in obstructed links. Thank you for listening.